Let's consider the second method of finding particular solution, the method of variation of parameters. So the first thing, again, as before, we have to solve corresponding homogeneous equation. And we get here n linearly independent solutions if A is n times n matrix. And from these solutions we can construct the fundamental matrix denoted by capital X of t. This is fundamental matrix. And in this case, homogeneous solution, as remember from previous lectures, we show that homogeneous solution is the fundamental matrix times some constant vector C, where C is a vector of C1, C2, and so on, Cn. The vector of constants. And second, what we do in variation of parameters, instead of this constant vector, we assume that this is some vector function. So we look for particular solution in the form, instead of this constant vector, we write some vector function. And we substitute this now into the equation. Let's say this is 1. What do we obtain? When we find the derivative, of course the derivative here, we will use the derivative of a product. So this is x prime of t v t plus x of t v prime of t, and this is equal to a times x of t v t plus f of t. And what we need to find? We need to find this v of t function. So what we have to see now, since x of t is fundamental matrix of the homogeneous equation, so we have that x prime of t, if we substitute in the homogeneous equation, this is equal to a times x of t. So x prime of t can be replaced with this thing. So this one and this one in the equation can be cancelled, and so we get that x of t v prime of t is exactly f of t. So to find v, we need to find the x inverse and multiply by x inverse the both sides of the equality. So we need to find capital X inverse, and of course it exists because the columns of this matrix are solutions of a homogeneous equation, and these solutions are linearly independent. So this exists since the columns of the matrix are linearly independent. So when we find this, what we do, we multiply both sides by x prime inverse and this will give us, of course, the identity matrix, and so our vector v of t is it should be prime. The derivative of v of t is x inverse of t f of t, and then finding v, we take the integral x inverse of t f of t dt, and now substitute into particular solution. Particular solution is x times v, right? So x of t times v of t, so times the integral x inverse of t times f of t dt. So this is precise formula for finding particular solution for this method of variations. And we will use this formula now in an example. So assume that we need to solve this particular system. Again, the first step as before, we solve homogeneous system. So the first step we solve homogeneous, so we need to find A minus Ri. We need to find eigenvalues. So 2 minus R minus 3, 1 minus 2 minus R. This is minus 4 plus, so the product of these two, plus R squared and plus 3, so we get R squared minus 1 is 0. So we have two eigenvalues, 1 and minus 1. For each eigenvalue we have to find eigenvector, right? So when R1 is 1, we find A minus, instead of R we take 1, apply to U1. This is the matrix 1 minus 3, 1 minus 3. Let's say U1 is x1, y1. This must be 0. So x1 minus 3y1 is 0, or x1 is 3y1. So we can take y1 to be s, to be the parameter. And so u1 is, x1 is 3s, y1 is just s, sorry, just s. So we get s 3, 1. And for the second eigenvalue, we have plus I here. So this will be 3 minus 3, 1 minus 1. Let's say x2, y2. And so we get from here that x2 is equal to y2. And so the eigenvector will be s1, 1. So what is the fundamental matrix? We first have to write two solutions, right? The first solution is e to the power eigenvalue, the first eigenvalue times t, so t times the first eigenvector 3, 1, and x2 is e to the minus t, the second eigenvalue, times the second eigenvector 1, 1. And what is the fundamental matrix in this case? We just take the columns of these two. Columns are x1 and x2, so the first column is 3 e to the t, e to the t, and the second column e to the minus t, e to the minus t. And now what we have to do, let's look at the formula. We have x of t, now we need x inverse of t, right? So this is what we're going to find. So how to find x inverse? We have to write the matrix and the identity matrix, and we have to do some row manipulations to get identity matrix on this side, right? So what we do, we write the first and we multiply this by minus 3 and add to this, so we get 0 times minus 3, add to this, we get minus 2 e to the minus t, times minus 3, add to this is 1, minus 3, add to this is minus 3. So now we need to get rid of this part here. So we write the last row. And how to get rid of this? We multiply this one by 2 and add to this one, right? Multiply this one by 2, add to 0 will give us 6 e to the t. This one by 2 adding to this will be 0. 2 adding to this will be 3. 2 adding to this will be minus 3. And now what we need to get ones on the main diagonal, so we just divide by these values here, so we get 1, 0, 0, 1. And when we divide the first row by 6 e to the t, we get 1 over 2 e to the minus t minus 1 over 2 e to the minus t. And dividing the second row by minus 2 e to the minus t, we get minus a half e to the t. And here we get 3 over 2 e to the t. So this will be our x inverse of t. So now the particular solution is x of t, 3 e to the t, e to the minus t, e to the t, e to the minus t, the integral of x inverse, so half e to the minus t minus a half e to the minus t minus a half e to the minus t, 3 over 2 e to the, to the t here. And this matrix is applied to the vector f. Let's have a look now what we should do. We should apply this matrix, multiply this matrix by this vector f, this vector function f. So this one here that we have, this is e to the 2t 1. So times e to the 2t 1 dt. Okay, let's find it. So when we okay, let me leave it like here, and the integral of what? When we multiply, we get a vector again, right? And the first term of this vector will be a half e to the minus t times e to the 2t. So this will be a half e to the t, right? Minus a half e to the minus t times 1. So minus a half e to the minus t. Then this is the first term of this vector. The second term, we multiply second row times this vector. We get minus a half e to the t. No, 3t, right? 3t e to the t times e to the 2t, we get e to the 3t plus 3 over 2 e to the t. This we need to integrate. So this is our matrix X. When we integrate, what do we get? So we obtain a half e to the t plus a half e to the minus t minus 1 over 6 e to the 3t plus 3 over 2 e to the t. So let's now multiply this matrix times this vector here. So 3 e to the t e to the, so e to the t, and this column e to the minus t, e to the t, e to the minus t times the vector, so a half e to the t plus a half e to the minus t and the second component is minus 1 over 6 e to the 3t plus 3 over 2 e to the t, minus 1 over 6 e to the 3t plus 3 over 2 e to the t, 3 over 2 e to the t. So when we multiply, we get a vector again, and the first component, this times this, right? So let's multiply 3 e to the t times the first component of the vector. So we get 3 over 2 e to the 2t plus 3 over 2. Then this times this, now this times this, minus 1 over 6 e to the 2t plus 3 over 2. Okay, this is the first component. The second component will be 1 over 2 e to the 2t plus a half minus 1 over 6 e to the 2t plus 3 over 2. So if we combine similar terms here, what we get? We have here 9 over 6 minus 1, so this is 8 over 6, or 4 over 3 e to the 2t plus 3. And this one is, so this is 3 over 6 minus 1, so 2 over 6, or 1 over 3 e to the 2t. And here we get just 2. So that's it. This is our particular solution. And let's now see. We have to combine now x1, x2, so homogeneous solution and particular solution. So our solution is homogeneous plus x particular, and the homogeneous was c1 e to the t some vector plus c2 e to the minus t some another vector plus xp can be written in more beautiful way. So 1 over 3 can be taken out, e to the 2t times this vector for 1 plus this constant vector 3, 2. Okay, let me just check the vectors for homogeneous. So these are 3, 1 and 1, 1. So 3, 1 and 1, 1. So this is general solution of the given system.